Good morning. Now we know how to take derivatives of sums, of differences, of products, and of quotients. An even more interesting way of combining functions is through something called composition. So this was something in pre-calc that you would learn. Two functions are composed if you put one function inside of another function. So h of x would be a composition of f of x and g of x. So as an example, if f of x is sine of x, g of x is e to the x, then we have that f of g of x is f of e to the x, or sine of e to the x. So again, this is a pre-calc concept. If you don't seem to remember how to do that, I would recommend doing a Google search for composition, just so that you have pre-calc tools, because what we're going to be doing is we are interested in finding derivatives of creatures like this. And to be able to do this, you need to have the pre-calc skills down. Okay, so let's assume then that you do have the pre-calc skills down, and let's look at an example that we can find the derivative of. So let's say h of x is equal to, 2x plus 3 to the third. And I asked you to take the derivative of this. Right now, you might be tempted to say, oh, let me just pull the 3 down and make that a 2. Except the power rule only is going to work if the inner function is x. Here, the inner function is a function of x. So let me convince you that won't work with another example. So let's say we have h of x is equal to 2x cubed. So let's say you say, oh, I can find the derivative of that just by using the power rule. Pull down the 3. So is that correct? Well, to convince myself whether this is correct or not, let me cube this out. Well, this is 8x cubed. So here I can apply the product rule and then multiply it by that constant. So I know for certain that h prime of x is 24x squared. But if we look here, we get 3 times 4x squared, and these guys are not the same. So that tells me that if I have a function inside here, I can't just apply the power rule. So I can't do that here. Well, is there any other way I can solve this? Sure, I could just cube that out, use the limit definition of the derivative, or actually, if I just cube this guy out, I'll have a polynomial and I can do it term by term. Great, except what if I then have a problem that looks like this? What if it's down to the 30th? I definitely don't want to multiply this guy out. So with that said, if I look at this from a larger perspective, I see that h of x is actually a composition of two functions. So maybe I can come up with a shortcut for the composition in general, and then apply this guy using a more generalized formula. So I'll give you a second, pause the video, make sure we're on the same page in terms of what f of x and g of x are. Right, hopefully you said, well, I'm sticking 2x plus 3, that's the little guy, I'm sticking 2x plus 3 into x cubed. So again, if that was, into x to the 30th. If that was challenging for you, you definitely want to review the pre-calc concept of composition, because we have to be able to do this first. This isn't the calculus part, this is actually the pre-calculus part of this problem. All right, so I recognize that it is a composition, so my goal right now then is to try to come up with a derivative formula for f of g of x. To get there, I need to do a little bit of prep work. I'm going to do the prep work over here. Let's note a couple of things. First, if h is close to 0, so these are just notes. These are things we're going to use in the proof. You're not going to see how we're going to use them, but we're going to use them in the proof that we have here. If h is close to 0, then g of x plus h minus g of x over h is approximately, I'll pause the video, see if you can answer that. And hopefully you said, oh, this is going to be approximately g prime of x because the definition of the derivative is the limit as h goes to 0 of this guy. Well, if that's true, then I can multiply this guy over here. So this is just algebra. And I can add this guy over here. So this tells me that g of x plus h is approximately g of x plus g prime of x times h. And I mean, that makes sense to me. So g of x plus a little bit is going to be wherever you were at g of x plus how fast the y terms are changing with respect to x times h, which is a change in x. So this guy is, I'm going to abuse notation a little bit here. It's not quite delta, it's actually a dy dx, but let me just call it delta y times delta x. And actually I can't say that now that I'm thinking about it because this is approximate, times my h, but my h is a delta x. So I'm taking the y value plus the change in the y value, and that's where I wind up at the end of that interval. Okay, so that's one note that we need. Again, you'll see why in just a couple minutes. We also can say that if k is close to 0, then f of z plus k minus f of z all over k is approximately, well, hopefully you're seeing the game here. This is now approximately f prime of z. So k is taking the place of h. It's just a different variable that I'm using because it'll help me out later. I'm using z instead of x. So we can play the same game. We could times this by k over here. We can add this guy to both sides. And then see if you could work out that algebra as well to get that f of z plus k is going to be approximately f of z plus f prime of z times k. Okay, so I'm going to use this result and this result in this proof. So pause the video, see if you can write out the definition of the derivative for this guy. Right, hopefully you said that's the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. So I'm just plugging in x plus h wherever I see an x. Well, for small h, f of g of x plus h minus f of g of x over h is approximately, well, let's take a look over here. If h is close to 0, then we have this result. So this g of x plus h that I see here, I can substitute the g of x plus g prime of x times h from over there. So this guy is approximately f of g of x plus g prime of x times h minus f of g of x all over h. Okay, so this is approximately this. So let me get rid of this stuff so we just have a little bit less to look at on the board. All right, so what I'm going to do now is I'm going to call the g of x, I'm going to call that z. And I'm going to call my g prime of x times h, I'm going to call that product k. So let's look over here. Well, first off, if h is close to 0, then g prime of x times h should be close to 0 as well, assuming g prime of x is a finite number. That tells me that f of z plus k is approximately f of z plus f prime of z times k. So you might need to pause the video at that step. That step's always a little bit challenging for students to match up the z's and the k's. Make sure you believe that, because if you believe that, then I can substitute f of g of x plus g prime of x times h with this guy. So I get f of g of x plus f prime of g of x, I'm just copying it down, times g prime of x times h. So that's this piece over here. And then I'm going to subtract off f of g of x all over h. All right, again, let me get rid of this stuff here because I don't need it anymore. Well, this goes away. H is small, but it's not 0. So this goes away. So for small h, this guy is approximately this guy. And the approximation gets better and better and better as h approaches 0. So that tells me that the derivative of f of g of x is equal to f prime of g of x times g prime of x. And this guy is known as the chain rule. The chain rule. All right, so let's go back to our original problem and see if we can apply this chain rule. Actually, why don't you pause the video? See if you can make sense of this formula with these two. So give it a shot. Well, hopefully you gave it a shot. Looks like I need the derivative of f, and I need the derivative of g. So let's see, f prime of x is 30x to the 29th. G prime of x is 2. And then let me plug these values in. So I get f prime of g of x, so f prime of g of x, which is 2x plus 3, times g prime of x, which is 2. So now I can plug this guy in here. So I get 30 times 2x plus 3 to the 29th times 2. So that's what the derivative is. Way faster than multiplying that out. Okay, let's try another one. Let's say h of x is equal to either 2x. So I'll give you a couple of minutes, or I guess as much time as you need. Just pause the video, see if you can mimic the process and come up with this guy's derivative. So in this case, you pause the video, you give it a shot. The big function is e to the x, and I'm sticking a 2x inside of that. F prime of x is e to the x. Derivative of e to the x is e to the x. G prime of x is equal to 2. So by our formula, we have f prime of g of x, or f prime of 2x, times g prime of x, or times 2. And I can plug this 2x in here to get e to the 2x times 2. So that's that guy's derivative. So this process is great at first, but I want you guys to be able to do these in your heads. So you might be thinking to yourself, whoa, there's no way I can do it this way in my head. You're absolutely right. Doing it this way is tough. I can't do it like that in my head. I can't remember f of x, g of x, f prime of x, g prime of x. But instead of doing it that way, what we're going to do is we're going to realize what this formula is doing and be able to actually think it through in our minds. From experience, I can tell you that for lots of students, this can take several days. But once you get used to it, it becomes second nature. And you want to get used to it because when we compute these derivatives, we don't want to have to go through this process every single time, especially when we're doing applications. So how do I think about this? So I'm looking at this formula, and I'm going to kind of say it in English. So I'm really taking the derivative of the big guy, leaving the little guy in there, times the derivative of the stuff inside. So I take the derivative of the big guy, keep the little guy in there, times the derivative of the stuff inside. So let's look here. I'll take the derivative of the big guy, so 30 blank to the 29th, leave the little guy in there, times the derivative of the stuff inside. Boom. That's how I think about it. Think of the big picture times the derivative of the little guy. Same thing here. This is e to stuff. The derivative of e to stuff is e to stuff, that's this piece, times the derivative of that stuff, times 2. So let me put one more example up on the board. So let's say about h of x is equal to 1 over 2x plus 1. Let me point out that you could do the quotient rule with this, because it is a quotient. I would never do the quotient rule. I avoid the quotient rule if I can, because it's always messy. So let's rewrite it like this, and now we see that this is going to be a composition. So pause the video, see if you can think this through in the process that I just described. If you can't, don't worry about it. Do the f of x, g of x business, but again, a strong encouragement on my part to develop an understanding of the process I just described. I would stick to that if you can. So pause the video, think it through. Okay, hopefully you said the derivative of stuff to the negative 1 is negative stuff to the negative 2 times the derivative of that stuff. Boom, we're done. All right, so today we looked at compositions of functions. This particular rule, I feel like it's the most powerful because it really enables you to combine functions in interesting ways that the other rules just can't do. With that said, that's the end of the chain rule. That's all I have to say for this lecture. Hope you enjoyed it, and I will see you next time.